This meeting is being recorded.
Okay, good morning. So I think the next topic that would be very good if we can actually learn a little bit about is the theory of matrices, matrix theory, yes? Because I don't know, for some reason in the Swedish curriculum, the students doesn't study about matrices at all. Okay, and I think this is a very important topic. I don't know, at least I think it would be good if a high school student have some familiarity with the matrix theory. Okay, so here I want to talk about matrix theory in an abstract level, more or less. I'm not talking about the applications and things like that. Of course, if you want, you can Google around and see what some videos on YouTube related regarding the application of matrices, which is of course a very broad range of applications. There are a very broad range of applications for matrices. But here I just want to keep it as an abstract level. I introduce you an object in mathematics called a matrix, and then we explore its properties and the relations, how we can in principle, I want to introduce you the algebra of the matrices. So, okay. Let us see how this goes. At least I will introduce you some concepts, and then we will decide later how much deep we can go into this theory, very important theory. Okay, so I started with a very simple motivating example, even though I told you that I'm not just working on the motivation part, I'm just introducing you the matrices as an abstract mathematical object. Anyway, it's better to have a motivation. So numerical information is often organized into rectangular tables. Yes, for example, if you consider the following table, this specifies the number of hours a student spends on homework in 4 subjects: mathematics, English, chemistry, and physics. For example, this student spent 2 hours for English on Monday. This student spends 2 hours for math, 2 hours for English, 1 hour for chemistry, and 1 hour for physics. And these are the other number of hours that is the student spend on these particular subjects on the other days of the week. Okay, usually the data in the table is important for us, not the headings and things like that. For example, Monday, Tuesday, Wednesday, we can have a convention that, okay, we start from Monday and we go to Sunday, and then the subjects are math, English, chemistry, and physics, and write it in one place as a guide, and then we can have these rectangular arrays for different students. So what at the end is important is the number that you collect in this rectangular object. If you have a rectangular object, if you have a rectangular array of numbers, that rectangular array is called a matrix. Yes, as simple as that. So when I talk about a matrix, I mean a rectangular array consisting of numbers. These numbers could be any type of numbers that you like, depending in which context you are working. These numbers even can be complex numbers, so it doesn't matter. Okay, so if I want to give it a little bit formal, so this session is a lot of information. There are many terminologies. I want to introduce hopefully all of them for you, because there is nothing hard at all. I'm just introducing some names for you. I want you to get familiar with the symbols, with the notations, the terminologies used in matrix theory. Okay, so if I want to give a little bit more official definition of a matrix, we say that a rectangular array of numbers is called a matrix. Okay, and its plural is matrices. Yes, if you have a bunch of matrices, yeah, if you have more than one matrix, this is called matrices. Okay, so each number located in a matrix is called an entry. This is the more common word. Of course, you can also call it element. Yes, but usually elements is reserved for the members of a set. Of course, it doesn't matter. I have seen both of them, but I will use mostly entry for these numbers that you see. Any one of these numbers that you see in this rectangle is called an entry of that matrix, okay? If a matrix has m rows, so for example here my matrix has 4 rows and n columns, so here 1, 2, 3, 4, 5, 6, and 7, then it is said to be an m by n matrix, or a matrix of size or order m times n. So when you see m times n, you don't read it m times n, you read it m by n. And then it is very important to note that this is a convention. The first number in this symbol, in this notation, refers to the number of rows, and the second number refers to the number of columns. It is a convention, okay? And then this notation is also good to know. So matrices are usually denoted by English capital letters. It's common to denote the entries of a matrix by the lowercase letter corresponding to the capital letter that denotes the matrix itself, together with two indices such that the first index indicates the row to which the entry belongs, and the second index indicates the column to which the entry belongs. So what do I mean? Let us, for example, consider this example. So as I told you that this session is more or less a presentation, because if I want to write all these things down, it takes time, but at the end of the day, it just transforms you a little piece of information. So it doesn't worth it if I want to write all of these. I have already prepared them. So this lecture would be more or less a presentation style. Okay, so each one of these that you see I have written here can be considered a matrix. So you see I am respecting what I told. Usually matrices are denoted by English capital letters. Of course, this is not universally adopted. So for example, in physics, there are many matrices. Physicists use even Greek letters or small alphabet to show the matrices themselves. Okay, but anyway, in mathematics, usually matrices are denoted by capital English letters. Okay, so if I ask you what is the order or what is the size of this matrix, it's important to say this has 3 rows and 2 columns. So this matrix A is of order 3 by 2, not 2 by 3. You need to respect this convention. The first number refers to the number of rows. The second number refers to the number of columns. So this matrix is a 3 by 2 matrix, whereas this matrix is a 2 by 3 matrix. 2 rows and 3 columns. So 2 by 3. If I ask you what is the order of this matrix, it only contains 1 row and 1, 2, 3, 4, 5 columns. Yeah, so it is a 1 by 5 matrix. This matrix clearly is a 3 by 3 matrix. And this matrix has 2 rows but 1 single column. It's a 2 by 1 matrix. This matrix has just one single row and 1 single column. So this is a 1 by 1 matrix. Okay, and then let me talk a little bit about the last sentences in that notation. I told you that if you call a matrix capital A, it is very common to call the entries with lowercase letter a. If I call my matrix B, I call the entries by lowercase letter b, and equipped with 2 subscripts. Yes, so for example here you see that I have written A sub 1 1. It means that I am referring to the entry of matrix capital A. This is the lowercase a. I mean capital letter A. So I'm referring to matrix denoted by the capital letter A, and I am referring to that entry which lies on the first row and the first column. Okay, so when I write A, I, J, I mean I am interested in the entry in the matrix capital A sitting on the ith row and jth column. So again, the first number refers to the row number, and the second index refers to the column number. That's also a convention. So here you see that, for example, let us just talk. I don't want to read all of them. A sub 3, 1, what does it mean? It means that I go to matrix denoted by capital A, it's here. I look at the third row and first column. Third row and first column. So intersection is this one, and that is -1. So this is why I have written A sub 3, 1 is equal to -1. Or, for example, I can go here. This is little c, so it means that I am referring to the entry of the matrix denoted by capital C. The entry is sitting on the first row and fifth column. So this is the first row and fifth column is equal to minus square root of 2. And if you have any questions, please interrupt me. So this is not something very deep. These are just conventions and notations. And of course, for the matrix F, this is the only one that I can talk about, yes? So the entry in matrix capital F sitting on the first row and the second and the first column, of course, that's clearly equal to 5. And of course, there is also another convention for this matrix, which is the topic of the next remark. So by convention, any 1-by-1 matrix is identified with its own entry. For example, the matrix F in the above example is simply written as 5 rather than square brackets around it equal to 5. So usually we do not have this. Whenever I have this situation, I simply say that matrix F is just simply the number 5, okay? But technically, that's a 1-by-1 matrix. Okay, and there is another, so if I want to talk about, that's also very good to know, a generic m/n matrix A is something like this. When I talk about a generic m/n matrix, capital A, what you need to imagine in your head is that you have a rectangular array of numbers, and then this one is the one sitting on the first row and first column. This is on the first row but second column. This is why the first index is still 1, the second index is 2. And if I go to the next one, this is the entry sitting on the first row and the third column. And I continue up to A sub 1n. Why n? Because I have mentioned that this matrix is m/n. So it means that I have m rows and I have n columns. So this is why if you see the last one includes an n, it means that all of these entries are lying on the nth column. And if you go to the last row, you see that all these row indices are m, referring that all of them are lying on the last row, which is m in this case. And of course, it is clear that the last one is sitting on the last row, which is m, and on this last column, which is n. So this is why it is denoted by this. Of course, if you want to prove theorems for matrices, writing and working with these big blocks is actually tedious and boring. This is why we compact all of this into a very compact notation and write that this matrix A, capital A, is a matrix. We denote the order as a subscript here. This means that this matrix that I am thinking about is an m/n matrix. And then I just write a typical entry inside my matrix, and I write an index I and j. So of course, it is clear that here I is a natural number which runs from 1 and m inclusive, and j is an index, a natural number which runs from 1 to n inclusive, yes? So whenever these entries are not that important, I am talking about the theory behind that. So I really don't need to bother myself to write this. I could just simply write this. So from now on, when I write this, I mean this block here. Okay? And sometimes it's also good to have another notation. And sometimes, of course, here, if I say A sub ij, sometimes it is good to have another notation. And that is sometimes we write the capital A and then we put a pair of brackets around that. And then I put sub ij. I use these symbols interchangeably. Okay, both of them are actually the same. So some books, they're also using this. They are saying that my matrix is called capital A, and I am interested in the entry sitting on the ith row and jth column. Either we can show it in that way, or we can show it in this way. And of course, I have seen some books put a pair of square brackets around that, and then they write this. So whenever you see this, or you see this, or you see this, all of them means the same thing depending to the book that you are using. But I want to stick to this notation, okay? Because I am reserving these square brackets for the big matrix itself. And when I want to refer to an entry, I think it is good to change the notation a little bit so that it is easier for us to differentiate between notations, okay? So for example, if I go back to example 2, if I ask you what is this one, this means that I am interested in the entry of the matrix capital A sitting on the second row and second column. So if you go back here, this matrix A, second row and second column, so the intersection is 0. So when you see this, actually, it means 0. And this means that the matrix B is interested. We are interested in matrix B here. The entry is sitting on the second row and third column. Yeah, so second row, and third column. So that is number 4. As easy as that. Okay, as simple as that. So, but this is very important. So whenever I write this, you need to imagine a block like that. Okay, so let me do these exercises. These are very, very simple ones. So I think it's better for me to do it without asking, because that's not a big deal here. So here, let this matrix, again, you see, by reading this piece of notation, I mean that I have a matrix A, it's a 2 by 2 matrix. The entries are given with A sub ij. So if someone asks, what is the meaning of this? You would say this is the entry sitting on the ith row and jth column. And they have mentioned that there is a formula for this entry sitting on the ith row and jth column. And the formula is this. This tells you that to calculate this, you need to raise the row index to power 2. You need to multiply the column index by 2 and then add these two numbers. So if I want to solve this, I would say that, okay, because you are telling me that A is a 2 by 2 matrix, it means that this is the generic form of that matrix. Yes? Oops, I'm also confused. So A2, 2. Is that understandable for everyone? So this is a matrix, a 2 by 2 matrix in general. The first index refers to the row number. The second index refers to the column number. So this is the general form. So now I need to calculate these things. So if I calculate A11, according to the rule given to me, here the row index is 1, the column index is 1 again. So this becomes the row index to power 2, 2 times the column index, and then added together. So if I calculate this, this becomes 3. And the next one is A sub 1, 2. So I need to square the row index. I need to multiply the column index by 2 and add them. So if I do, this becomes 5. And then this A21 is 2 to the 2 plus 2 times 1. The answer is 4. And finally, A22 is 2 to the 2 plus 2 times 2. So the answer is 8. Yes? So this means that what this problem asks us to do is to write this into complete form. So the first entry I calculated 3, the second one is 5, the next one is 4, and the next one is 8. Yes? Yeah, so I will not ask you, do you have any questions or not?
not-
Whenever you have questions, please interrupt me.
Babak,
Any question? Yes?
it's not 4, it's 6.
Where? Yeah, thank you very much. Thank you. Here, you mean. Yes, thank you. So I should change this one as well. So is that correct now?
Yes.
Okay, good. Thank you very much. The next problem is also the same, but this time my matrix is a 2 by 3 matrix. I call the matrix capital B and the entries are little b. So if I want, but of course the formula has two rules depending on the values of the row and column indices. Yes, so what we can write is that, okay, you are telling me that this matrix B is a 2 by 3 matrix, so it means that it has 2 rows and 3 columns. So if I want to write it, I should write it in this way. So it is B1 1 and the next one is B1 2. This row index is kept the same and I am changing the column index. Yes, and the next one is B21, B22, and B23. Okay, I need to calculate these things. Okay, how should I calculate B11? So when I go here, it depends. If the row index is equal to the J index or greater than the J index, then I need to use this rule to calculate Bij. But if the row index is smaller than the column index, is less than the column index, then I need to divide the column index by the row index. So that's the rule, okay? So here B11, because these two are the same, I need to follow the first rule. So it becomes 1 minus 1, and the answer is 0. But when I go to the next one, here the row index is 1, the J index, let me write the I and J. I index is 1, J index is 2, so I index is less than J index. So I need to divide the J index by the row index, and this becomes 2. And please, again, if you are making mistakes, because these are so simple, I don't know, my brain doesn't pay attention that much to it, okay? But if you please correct me. B13, what happens is I have the same scenario, so I will write 3 times divided by 1, so the answer is 3, and then I go to the next one, B21. Here, the I index is greater than the J index, so I have to write 2 minus 1, which is 1, and then when I go to B22, these are the same. I have to use the same rule again, so this is 0, but when I go to 23, here I is less than J, so I need to divide J by this one. And I can keep it like this. So B is this matrix. Is 0, 2, 3, 1, 0, 3 over 2. So that is my matrix B. Any questions? Okay, good. We go to the next example. So these double sigmas and double sums are actually ubiquitous when it comes to a little bit higher level matrix calculation. This is why I just introduced you here. So I want to see this matrix is given to you and you are supposed to calculate these two double sums, okay? The reason that I'm calling it double sum because I have two sigma notations. And you see that one of the counters, one of these sigmas has J as the counter and one of these sigmas has I as the counter. And this is understandable because what is inside these double sum is something which depends both on I and J. Yes, and here you see I have written exactly the same thing. The only difference is that I have interchanged these two sigmas, and my goal is to show that this will not affect our calculation. The way we calculate is different, but finally we get the same answer. So whenever from now on we have finitely many sums, you can change these two. You can interchange these sigma notations, symbols, if you want to, okay? But let me calculate this one. So let me calculate one of them for you. So by the way, there are two ways that you can even calculate the first sum. Let me just concentrate on that one, and then you can do the next one as an exercise for yourself. Here, I can interpret it in two ways. I can consider this and then say that, okay, I first open the first sigma and then I will open the second sigma, or the other way around. I can say that, okay, first I open the first sigma and then I apply the second sigma. Both of them are actually the same. So here, let me first do the inner sigma. So what does this mean? This means that I do not touch the first sigma, but I open a pair of brackets and I want to open up this sigma. So this sigma depends only on j, and j runs from 1 to 3. So it means that here, instead of j only, I replace it with 1, then replace it with 2, and then finally with 3, and then add them. But I'm not touching the I index. So this becomes I1, and then I will have I2, and then I will have I3, yes? But now I open the second sigma. The second sigma, I goes from 1 to 2. So it means that I need to replace I with the first number 1 everywhere. So what I get is this. It becomes A11 plus A12 plus A13. And then I do the same thing. This time I choose I equal to 2. So this becomes 2, 1 and plus 2, 2 and plus a 2, 3. And then add these two together. So that's very simple. But now if I ask you what is this number, you need to refer to this matrix. And these are all entries on the first row. First row, first row, first row, because the first index is 1. The first column, second column, third column. So it means that these are these numbers. Yes? So it is easy to see. So the answer here, let me write on top so to save some space. So here, this becomes 1 plus 2 plus 3, which is 6. And then here, these are on the same columns, 1, 2, and 3, but all of them lie on the second row. Yeah, so these are 2, 1, and 0. 2, 1, and 0. So this becomes 2, 1, and 0. If I add them, it becomes 3. And now if I add these two numbers, so finally my answer is 9. Okay, if I want to interpret it in a different way, so I can calculate this sigma, but I can open the first sigma first, on the first sigma on the left first. So what does it mean? It means that this is an expression. The j index is running from 1 to 3. So at the end, what is left here, the dependency on I will be left. And this is acting on that dependency, yes? So this means that if I want to open the first sigma on the left first, I would write sigma, j goes from 1 to 3. Instead of I put the first number, which is 1, and then I would write j. And then I will go to the next one. I would write sigma, j goes from 1 to 3 again, but this time I switch I with 2, so it becomes 2j. See? I wrote this expression once I equal to 1. This gives me the first one. I wrote this expression for I equal to 2. It gives me this one. But now this is a sigma. This is a sigma. Both of them only depend on j. And then I open the first sigma. It becomes A11. I'm changing j from 1 to 3. It becomes 1, 2, and then 1, 3. And the next sigma becomes A21, A22, and finally A23. And then, of course, the answer is 9 again, because there is no difference between these two pair of brackets. Okay, and then you can do this one yourself. I think that's a very simple one. But again, you will get the answer 9 independent of the way that you interpret it, okay? So then the take on from this lesson would be that it doesn't matter if I interchange these two finite sums, the answers are the same. Okay, now the next definition should be very expectable for you. You should expect that this definition should come, because whenever I am introducing an object in mathematics, first I want to say that when these two objects are the same. And of course, usually the most natural intuition is the correct one. So I give you two blocks of numbers, two rectangular array of numbers. When do you expect that these two blocks defined to be equal? Okay, they are exactly identical blocks. So it means that they have the same number of rows, they have the same number of columns, and of course, each entry from one of them equals to the corresponding entry of the other one. That is the meaning of two matrices being equal intuitively. Okay. So there is a typo here. There is no hence. So two matrices are said to be equal if they are of the same size, meaning they have the same number of rows as well as the same number of columns, and their corresponding entries are equal. We write A equal to B to denote that matrices A and B are equal. So for example, consider the following three matrices. The matrices A and B are equal only if X is equal to 4. Yes? I am asking you, is it possible that this matrix becomes equal to this matrix? First, you say that yes, because this is a 2 by 2 matrix. That is also a 2 by 2 matrix. So from order perspective, they have the same size. But this is not enough. Each entry should match with the corresponding entry, which is correct for 2. It's also correct for 1. It's also correct for 3. But for these two matrices to be equal, the last one should also match with the last one. So it means that X has to be equal to 4. So yes, if X is equal to 4, these two matrices are equal. Okay, but there is no X for which A and C be equal, because this is a 2 by 2 matrix, this is a 2 by 3 matrix, so there is no way to match them. Okay, so this is not possible. Okay, and then I don't know, these are very, very simple things, but it becomes more interesting in the next, from the next actually session. Consider following matrices. I have given you two matrices. If A is equal to B, determine X to the 3 minus 2y squared. Okay, a very, very simple exercise. So you are telling me that A is equal to B. I am sure that the orders should match. I should be certain that the orders match, which is of course the case, because this is a 2 by 2 matrix, 2 rows, 2 columns, and here is also 2 rows and 2 columns. So from the order point of view, they are the same. They have the same order. But then this implies that the entries should correspondingly match. So it means that X squared should be equal to 4, X plus 3 should be equal to 2X plus 1, 3X plus Y should be equal to 2X plus 2Y, and minus 1 should be equal to minus 1. The last one I don't need to bother at all, because that's true, but I need to be careful about satisfying all of these three simultaneously. But be careful, we have only 2 unknowns, 3 equations. So we have one more piece of information, but I need to satisfy all of them. So I would say that for the first one, there are 2 possibilities. Either X is equal to minus 2 or X is equal to 2. Okay? But from here, when I solve the equation, I move 2x to the left, it becomes minus x. I move 3 to the right, it becomes minus 2. So this becomes x equal to 2. So it means that if I want to have this and this and this simultaneously, so this means that from these two, it is clear that the answer so far is 2. X cannot be X cannot be equal to negative 2, because negative 2 makes this right, but not this one. I need both of them. And then when X is equal to 2, I will take this one and put it here and find Y. So this implies then 6 plus y is equal to 4 plus 2y, and then you get y is also equal to 2. Yes? So then the question mark is x to the 3 minus 2y squared, so it becomes 2 to the 3 minus 2 times 2 to the 2, which is 0. So the question mark in this case is 0. So you see that this is a very, very simple exercise. Any question? Okay, now there are a lot of jargon terminologies. You need to know these words. So this is just introducing some words, some definitions. These are very ubiquitous in matrix theory. So when we say a row matrix, when we say a column matrix, what we mean. Intuitively, it is clear for you, isn't it? A matrix that has one single row is called a row matrix, like this matrix. This matrix has one single row. So a capital A is a row matrix. This is the name that you need to remember. I will use, for example, in some problem, I would say that, okay, let A be a row matrix. Then you need to realize what I mean by a row matrix. And then a matrix containing one single column naturally is called a column matrix. For example, this matrix B is a column matrix because it includes only one single column. Of course, if you see here, this is, of course, if you remember, this is actually a number. But if you insist to write it as a matrix, this contains one single row, so it is a row matrix. It also contains one single column, so it's also a column matrix. But this is an extreme case, and it's not very interesting. So whenever usually we talk about row matrix, we mean a matrix more than one. Having one row, more than one column, having one column more than one row, that's 4-column matrix. Okay. So here I have another definition. It's called a zero matrix. I have here, you see, I have emphasized a zero matrix because there is no one single unique zero matrix. Zero matrices can be of different orders. Okay. So a matrix whose entries are all zero is called a zero matrix. But now I am saying the zero matrix of size m by n is denoted by this symbol O for the zero sub m by n. So as soon as I fix the order, then I have to use the article the, yes? But if this is not fixed, because there are infinitely many zero matrices, I should say a zero matrix. So here you see that I have examples of zero matrices. I have here a 2 by 2 zero matrix, 2 rows, 2 columns. Here I have a 3 by 1, 3 rows, 1 column. And here I have this one and this one. So you see this is a column matrix. This is also a row matrix. So you can play around with these concepts, okay? So how many zero matrices are there? There are infinitely many zero matrices of different order. But if I fix the order, then there is only one unique zero matrix, very naturally, yes? So the point is that all the entries, all of them, without exception, should be zero. If that's the case, you are facing a zero matrix. Okay. Another very important terminology in matrix theory is the notion of a square matrix, but this is so intuitive, so even if I don't define it for you, you still immediately can guess what I mean, yes? So a square matrix is a matrix whose number of rows and columns are exactly the same. So my block, my rectangular array is no longer a real rectangle, it's a square, and that I will call it a square matrix. So a matrix in which the number of rows and columns are equal is called a square matrix. Square matrix that has n rows and n columns is called a square matrix of order n. So when I say that I have a square matrix of order n, so it means that my matrix is n by n. Okay, and then because both of them are the same, I usually don't say n by n, I would say a square matrix of order n. And these are examples, yes? So this is a 2 by 2 matrix. It's a square matrix. This is a 3 by 3 matrix. And then here, this is a 4 by 4 matrix. Okay. So what we learned so far, row and column matrices, zero matrices, square matrices. Yes, so we learned about these three. We continue. There is another terminology that I want you to know in matrices: major and minor diagonals of a square matrix. Okay, I will come back to this point. So assume that I have a square matrix. If you see, this is a square matrix. Why? How do you see by looking at this why this is a square matrix?
Because the index on the last one it's n.
Yes, exactly. The last one is n, so it means that this has n rows because the final row index is n, and it has also n columns. Why? Because this is the way that I see it. The last index is the n index. So this is an n by n matrix. And then what I'm saying is that these entries, this is called the main diagonal of this matrix. So the entries on this diagonal are called the entries of the main or major diagonal of a matrix. Okay? And the entries lying on the other one, I haven't mentioned here, I have written it in words, but if I want to draw it schematically, this one, the entries here, 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 and up here, this is called the minor diagonal, okay, of the matrix. Okay, so so these are the entries lying on the main diagonal. These are the entries lying on the minor diagonal. Yes, but this is a remark. You know that if I have a rectangle, I can also talk about diagonals. Yes, this is not necessary only to have squares. Of course, if I have squares, I can talk about diagonals as well. But in geometry, if I have rectangles, I can still talk about diagonals. But this is not the case in matrix theory. Yes, so this is the content of this remark. Major and minor diagonals are defined only for square matrices. So this is, don't mistake about this. So in geometry, rectangles also include diagonals, but this is not for rectangular matrices. So whenever I talk about minor and major diagonals, it means that I am considering a square matrix. That's it. So even though I have written, of course, even though we can talk about the diagonals of a rectangle, but diagonals of rectangular matrices are not defined. That's that remark. This remark is also, I'm just not pushing you to memorize that, but I want to, by writing this as a remark, I want to draw your attention to it. Okay, so let me just here, I think it's good to draw a schematic here. So here, assume that I have a matrix. It's an n by n matrix. Okay. It's easier to have it in this form in mind. Okay. So here, this row, let me change the color. So here, this is the main diagonal. So, and what are the properties? Can you see? Let us make it a little bit smaller. Can you see what are the properties of all entries that lie on the main diagonal? What is the common property of all of them?
Their I index is the same as the J index.
Exactly. So the I index is equal to the J index. So let me write here on top. So here I index is equal to J index, its main diagonal. Okay, and then here below this, if I want to compare the I and J indices below, if you see here, if I am below here, all these entries that are below, the row index is greater than the column index. So it means that when I go below the main diagonal, I have I greater than J. Okay, and of course, if I go above the main diagonal, I is smaller than j. And let me, if you don't mind, let me clean this. You already know this is the main diagonal. So this schematic, it's good to have in mind, and that's the content of this remark. Aij is on the main diagonal if and only if I is equal to j. It is above the main diagonal if I is less than j, and it is below the main diagonal if I is greater than j. If I want to say something similar for the minor diagonal, what can I do? So I will do, oops, well, let me just draw it without using this feature. So again, here this is n by n, but this time this is my minor diagonal, okay? And then here, can you tell me what are the properties of all the entries sitting on the minor diagonal? You need to work a little bit to convince yourself about the truth of what I have written in this remark, yes? And so the point is that the sum of these indices are always equal to n plus 1. You can convince yourself by writing some particular ones, for example, 2 by 2, 3 by 3, and 4 by 4 cases. And you see that when you look at the entries on the minor diagonal, this is not the case that there is a very specific relation between these two. But if I add these indices, all of them becomes n plus 1. So let me just write it here for you. So here I have a11, a12, a13, a21, a22, a23, and another one a31, a32, a33, yes? So if I consider the minor diagonal, you see that 1 plus 3 is 4, 2 plus 2 is also 4, 3 plus 1 is also 4, and 4 is one more than the order of my matrix. My matrix is a 3 by 3 matrix, but when I add these indices, it becomes 4, which is 1 unit bigger. So I think you can immediately convince yourself that this is true. So let me write here. If I want to write, this is I plus j is equal to n plus 1. And if I go above the minor diagonal, you can immediately see that this becomes smaller. And if you go below the minor diagonal, it becomes 1. Now, I don't want you to memorize this at all, but I want you to understand that sometimes it is good to have these relations or to discover these relations when it is necessary. Any questions? Okay, so let us go to the next one. Another definition, which is also a very important definition in theory of matrices and a little bit confusing, are the notion of upper triangular and lower triangular matrices. So let me just tell you what happened. I defined you some matrices. They could be square matrices, of course, but they could be square matrices or rectangular, but then I defined you the notion of a square matrix. For the square matrix, the first thing that I add to it was the notions of minor and major diagonals. And then I want to talk about different types of square matrices, because mainly square matrices are the very important matrices, okay? Of course, rectangular matrices are also important, but the class of square matrices are important. So I'm talking about subclasses of square matrices. One of those that are important and are upper triangular and lower triangular matrices. A square matrix, this, is said to be an upper triangular if I sub ij is 0 for all I greater than j. This is the mathematical defining way. So it means that if I is greater than j, a sub ij is 0. So if I go back to the previous schematic here, if I is, so what was that? If I is greater than j, so it means I am here. Everything is here is 0. So it means that you see a bunch of zeros below. This is not called lower triangular. So the adjective upper refers not to the zeros, but to probably non-zero ones. So don't get confused here. So when we say upper triangular, we are not referring to where the zeros are sitting. We are referring to where the probable non-zero entries are sitting. Okay, so if all the entries below the main diagonal is 0, the matrix is called upper triangular. And if all the entries above the main diagonal is 0, the matrix is called a lower triangular matrix. Okay, so don't get confused because of this adjective. This adjective is not referring to the zeros, it's referring to the probable non-zero entries. Okay, so the following are examples of upper triangular matrices. Why? Let us check. I want to check that this A is an upper triangular matrix. I draw the main diagonal. I look below it. I should have everything 0 below it. If this is the case, I would say this is an upper triangular matrix regardless of the value or values of the entries on the main diagonal and above the main diagonal. Okay, so when I want to check if a matrix is an upper triangular matrix or not, I just draw the main diagonal and just look below it. Everything should be 0. If that's the case, I don't even bother to look at the entries at the entries on the main diagonal and above it. That's true. So here again, is this an upper triangular matrix? Yes, because if I draw this line, everything below is 0. Is this an upper triangular matrix? I don't get confused. I see a 0 here, but who cares? I just draw a main diagonal, I look below it. Everything below it is 0. And here again, I draw this, everything below is 0. So that's an upper triangular. This is also interesting. Is it an upper triangular matrix? Yes. Because when I draw this main diagonal, everything below is 0. And is this an upper triangular matrix? Yes, if I draw this, everything below is 0. Of course, these are extreme cases because these two examples are also a lower triangular matrices, yes? And then these examples are lower triangular matrices. So when I want to see if this is a lower triangular matrix, I draw the main diagonal. Everything above that should be 0. And this is the case, so this is a lower triangular matrix. So let us go here. I draw this, everything above is 0. So that's a lower triangular matrix. Of course, in this case, that's also an upper triangular matrix. Okay, so I don't think these are hard things. So matrices E, F, I, and M and N in the last two examples are both upper triangular and lower triangular. Any questions? Okay, let us go and solve this problem. Let us see how much is left. So I can give you 2 or 3 minutes. I think you can solve this problem. I'm talking a lot today. Yeah, so you can just think a little bit about this problem and solve it. I will come back and we can solve it together again. Did any one of you get the answer?
I started very recently on.
Okay, so because I want to finish this part, so if you don't mind, let me start solving it. But I think these are very simple things, okay? So I have a 3 by 3 matrix for which the entries are given with this formula. Of course, this is not one single formula. Depending on the size of I and j, I have to use different rules. But I want to determine this alpha, parameter alpha in the problem so that this matrix become an upper triangular matrix. Okay, so what does this mean? So if I have a 3 by 3 upper triangular matrix, what I know is that if this is the main diagonal, everything below is 0. So I have 3 zeros here, yes? So let me write it more properly. This is not a good way. So let me, might be I'm going fast. So I would write it's a 3 by 3 matrix. So it is A11, A12, A13, A21, A22, A23, 831, 832, 833, yes? So here, the main diagonal is this one. Everything below the main diagonal should be 0 because I am demanding my matrix to be an upper triangular matrices, to make matrix. So it means that what is below the main diagonal should be 0. So A is an upper triangular matrix. So this implies that A21 is equal to A31 is equal to A32 is equal to 0. Okay, but how can I calculate A21? So A21, because the I index is greater than the J index, I have to use this formula. And then alpha is alpha, but J in this problem, in this entry is 1. So I replace J with this 1. There is no I dependency here. So this means that alpha squared minus 3 alpha times 1, because J is 1 here, plus 2 times 1 to the 2 is 0. But this is a simple quadratic equation. You can use PQ formula, ABC formula, but I prefer to factorize it here. It's easier. I need two numbers whose sum is minus 3 and the product is positive 2. So these are the numbers. So equal to 0 by 0 product rule, it tells me that either the first one is 0 or the second one is 0. But I also know that A31 is equal to 0. But what is A31? A31, again, the I index is greater than the J index, so I have to use the formula, the first one. And then I need to replace J with this J, but J is again 1, so I will get the same equation. So it becomes alpha squared minus 3 alpha plus 2 equal to 0. So it will give me the same answers. Yes, but also I need A32 to be equal to 0. This means that which rule should I use? Oh, again, I have to use the first rule, yes, because the I index is 3, the J index is 2, and I is greater than J, so I have to use this. And this time I have to replace J with the J index, which is 2 in this case. So this gives me alpha squared minus 6 alpha. And then if I put 2 here, it becomes 8, yes? And let us use again factorizing method. So I need two numbers whose sum is minus 6 and the product is 8. So it is minus 2 and minus 4 equals to 0. So this means that alpha is equal to 2 or alpha is equal to 4. But I want to have all these conditions met simultaneously. Yes, I want to have this and this equal to 0. So the only number that I can choose is 2, yes? Because if I choose alpha equal to 2, all of them will work. But if I choose alpha equal to 4, this will work, but neither these two, yes? So this means that finally the answer to this problem is just simply alpha is equal to 2. Any questions?
No.
Okay. And then another class of very important square matrices are matrices which are called diagonal matrices. And I think that you already know what is that. A matrix is called a diagonal matrix if it is both upper triangular and lower triangular. In other words, it's a diagonal matrix if everything above, every entry above the main diagonal, as well as every entry below the main diagonal is equal to 0. Okay, so the examples that we had before, E, F, I, M, and N, in these previous examples, yes, you see, this is a diagonal matrix. Because if I draw this line, everything above, as well as everything below is 0. So it's a diagonal matrix. This is also a diagonal matrix because everything above as well as everything below is 0. That's also a diagonal matrix for the same reason, yes? So the generic form of a diagonal matrix is this. Here, this is common. When we put a capital 0, it means that everything here is 0. And again, the same story here. So this is in matrix theory. This is very common. If you see something like this, it means that we don't know something about these in particular, but we know that everything above is 0 and everything below is 0. So this is why we put a big 0 there. And there is another piece of notation that I want you to learn. And this is the notation that I have written at the very end here. So of course, this is also a good way to write a diagonal matrix, but you see that everything here is 0 and everything here is 0. So if I know that that's diagonal, I really don't need to emphasize on these two. So I would say that I use diag for diagonal, and then I just write the elements on the main diagonal from the first one to the very last one. So whenever you see this symbol, this notation, it means that that's a matrix. It's a diagonal matrix. You look at the last number, it is n by n diagonal matrix. And these are the entries lying on the main diagonal, yes? And that's it. For example, by the way, there is also another class of square matrices, but this is a class of diagonal matrices that is called a scalar matrix. Yes, a diagonal matrix that is its main diagonal entries are all the same numbers called a scalar matrix. So here, if I have a diagonal matrix and the entries on the main diagonal are all equal, then of course this is a main diagonal, but there is another more specific name, and that is called a scalar matrix. So a scalar matrix is a diagonal matrix whose entries sitting on the main diagonal are all equal. If that is the case, that matrix has a more specific name, and that is called a scalar matrix. So, and then you know that based on what I told you about the notation, another way to denote this is to write diag 3 and 3. So this means that that's a diagonal matrix, but when you see both of them are equal, so you can just write diag 3 and 3. And for this matrix, you can write this. And for this matrix, for the same reason, you can write this. Any questions? So these are the names that you need to know. So somehow by working them or memorizing them, you need to know these names. Now, a subclass of a scalar matrices, which are very important, has a prominent role in matrix theory, are called identity matrices. Okay, a scalar matrix that its main diagonal entries are all equal to 1 is called an identity matrix. And this letter I in matrix theory is reserved for the identity matrices. And we put a subscript n if that is n by n. So this is good to know. I sub 1, this is the identity matrix of order 1, this is the identity matrix of order 2, identity matrix of order 3, and identity matrix of order 4. All of them are scalar matrices, but the entries are all equal to 1. This is important to remember. This is a very important matrix in the theory of matrices. And the reason that this is called an identity matrix, it's playing something similar, playing the role something similar to the number 1. If you have a number, you multiply it by 1, it gives you the same number back. And now we will learn later that if I have a matrix and I multiply it by the identity matrix I, it will give me the matrix, the same matrix back. This is why it's called an identity matrix. So yeah, any questions? So these are very important different classes of matrices. This is just names. These are just names that you need to understand. Okay, so and then what I want to talk about, I was not quite sure if I want to talk about this to you because this is a little bit more advanced. It appears in more advanced texts, but I think it's simple. So at least it's good to know the name, okay? Kronecker is a mathematician, and this is called Kronecker delta. Kronecker's delta is denoted by this symbol. This symbol that you see here is the Greek letter delta, lowercase letter. The capital one is this just triangle. So this is delta, and with two indices I and j, where I and j are positive integers. It seems a little bit artificial why this is important. I will try to give you some idea why this is important, but that's a very important symbol in mathematics, okay? We define delta sub ij to be either 1 or 0. Very, very simple. It's not a very deep or conceptual thing. It becomes a very important tool later if you go to advanced mathematics. But here, it tells you that if the indices I and j are equal, the output of Kronecker's delta is 1. If the indices are not equal, the output is 0. As simple as that. So for example, if I ask you what is delta sub 1, 2, it's 0 because 1 and 2 are not equal. If I ask you what is delta 2, 1, you will say 0 because 2 and 1 are. What is delta 4 and 9? It's 0 again. What is delta sub 1, 1 or delta sub 5, 5 or delta sub 9, 9? All of them are equal to 1 because the indices I and j are equal. As simple as that. So if in principle, if I ask you what is delta mm, I really don't need to know the value for m. As soon as I see that these are the same, I would say that delta mm is definitely 1. And then of course it is clear that this is not sensitive to interchange of the indices. There is no difference between delta mn and delta nm. Why? Because there are two cases. If m is equal to n, the left-hand side is 1, the right-hand side is also 1. If m is not equal to n, the left-hand side is 0, the right-hand side is also 0. So it doesn't matter. In these two symbols always match, regardless of the value of m and n. So this is a symbol which is not sensitive to interchanging the indices. Okay. Yeah, let me just give you an exercise. It seems a little bit artificial. I'm just giving you this example to just work a little bit with this symbol to remove this mystery part of it. It's just very simple one. I have given you a matrix here, and the order is 1, 2, 3, 4. So this is 4, and 1, 2, 3, 4, 5, 6, 7. So it's a 4 by 7 matrix, and I have asked you to calculate these sums. Okay, so what can I do? It's very simple. Let us open the sigma. So I have sigma k goes from 2 to 6, a sub 2k, and then I have the Kronecker delta 5, k5. So what is the meaning of sigma? It means that I need to replace k with 2. Yes, and then replace k with the next number. And then replace k with the next number. Replace k with the next number. And finally, the last number. Yes, and then whenever I found the answers, I add them. But you really, what the point is that if you have this Kronecker delta inside your sigma and one of these indices is the counter of the sigma, you really don't need to expand this sum, yes? Because immediately it is clear what is the answer to this one? 0. This is also 0 because 3 and 5 are not equal. This is also 0. 4 and 5 is not equal, are not equal. This is also 0, but this one is equal to 1. Okay, so it means that when you have this delta under the sigma sum, actually this delta kills this sum. Only one term will survive, yes? And the term, which term survives? The term for which these indices become equal. And when these indices become equal, this delta becomes 1. So when you have this, you really don't need to calculate at all. You can just drop this sigma and you can just drop this delta, but you need to know that you have to switch k to 5 because the fifth term will survive. Okay, so I'm just telling you that that is not a very deep thing. What happens is that this, and this are all 0. I even don't need to check these numbers, yes? But this one has 1, so what is here? I will have a sub 2k. Oh, sorry, sub 2, 5. And then what is the answer? I go to my matrix, the second row, fifth column. Second row, 1, 2, 3, 4, fifth column. So the intersection is 1. So the answer to this is simply 1. Yes? Okay, so for example, what will happen? Can you, before expanding this, can you tell me what will happen here? Look at this number 7 here and look at the range of your counter.
It will be 0.
It would be 0. Everyone agrees? Because k goes from 2 to 6, but this index is 7. So it doesn't matter, yes? This k is either 2, 3, 4, 5, 6. It cannot be more than that, yes? Because this is the maximum limit. So if 2, 3, 4, 5, 6, all of them are different from 7. So I really don't need to expand anything at all. I can immediately say that the second sigma, of course, if you expand, you will get the same answer, but that's the whole point. I'm telling you that you really don't need to do that at all. Just by a little bit of thinking, you can save a lot of calculation, and you can immediately say that this is 0. Okay, now can you tell me what can happen here? You have something here, you have a sigma here, k goes from 1 to 7, and then you have delta k 3. Is there any term that will survive in this sum? Please answer.
Yes.
Yes, corresponding to which value for k?
For the value where k is 3, I guess.
Yes, and do you agree that if k is not equal to 3, from 1 to 7, I have 1, 2, 3, 4, 5, 6, 7. If k is 1, this becomes 1, 3. They are different. For 2, 3, so 1, 2, 4, 5, 6, 7. All of them are different. So there is only one term that will survive here. So sigma k goes from 1 to 7. So let me write something in front, and if you don't understand, tell me that I can explain it once again. So what I want to write is this. Yes? Is that understandable? Because I am expanding this sigma. If k and 3 are different, this is 0, and this means that the term corresponding to that value vanishes. So it means that the only term that I can expect to survive is when k becomes 3. When k becomes 3, what happens for this? This becomes delta 3, 3, which is 1 by definition, and then I need to replace k with 3. So I really don't need to write all 7 terms. Immediately, I can realize that this will shrink into only one single term. And then, of course, then I will read these two. What is A1 sub 3? The first row and the third column is this is first row, third column is 2. So the answer is 2 to the 2 plus 2 times 2, which is again 8. Questions?
Nope.
Good. And there is one piece of information left I want to cover today, and hopefully, so this is actually, I remember when I wanted to cover this, I write it on the board. I think it was 3 sessions I just writing these informations. And I hope that you agree with me that these are, although important informations, but it is very easy and easy to digest because most of them are names and terminologies. Another important point in a matrix, and I will probably talk a little bit about that if I have time. Why trace of a matrix is important, okay? And what is the definition of the trace of a matrix? And this is also a notion which is defined for square matrices. So let A be a square matrix. The trace of A, which is denoted by this symbol, TR of A, it is defined to be the sum of all main diagonal entries. In other words, if I have this matrix, a square matrix, otherwise main diagonal doesn't make sense. If I ask you what is the trace of A, you would say that I add the entries on the main diagonal. I get a number. That number is called the trace of my matrix. Okay, so it means that A sub 1, 1, A sub 1, 2, A sub 1, 1, A sub 2, 2, up to A sub n. Yes, that was, do you remember, the main diagonals have these two indices the same all the time. Okay, and of course, if I want to write it in a compact form using the sigma symbol, I can write A sub I, where I goes from 1 to n. So it's very simple. So for example, if I give you this matrix and I ask you calculate the trace of this matrix, you just need to know what are the entries on the main diagonal and just add them. Yes, square root of 3, 2, minus 4, and a square root of 3. I am adding these numbers. Square root of 3, a square root of 3 is 2 square root of 3, and 2 minus 4 is minus 2. So this number that you see is called the trace of your matrix. And then, for example, if the identity matrix IN, do you see that the trace of IN is n? Yes? Because do you remember, do you recall what is the identity matrix IN? Is the matrix whose is a scalar matrix whose entries are 1 all the way. Yes? How many ones are there depending to the order of matrix? Because you see this index n, it means that my matrix is an n by n matrix. So it means that I am adding these ones together. How many of them are there? N. So when I add n ones together, the answer is n. So the trace of the identity matrix IN is equal to n. So nothing conceptual is going on. I am just introducing you a lot of words. So I will upload the link. I will upload this to the Google Drive, and I give you the link below this video on the YouTube channel. So please download it and try to remember these. I'm also working on some exercises. And I have already talked a lot about these things. If you think that this is a little bit fast, I will also put some links from my own YouTube channel that I am talking about matrices. And because there I am writing on the board, so my speed cannot be very fast. So you can follow if you have some questions here. Any questions? Okay, so let me just stop this.